Sir Jon Keating, who is a Sedlerian, if I'm not pronouncing maybe properly, Sedlerian professor of natural philosophy at the University of Oxford. He's a prolific researcher who has worked in both mathematics and in physics, in quantum chaos, random matrix theory, and number theory. The list of awards he has received is long. Let me just talk about a few of them. He has been a fellow of the Royal Society of London since 2009. In 2010, he was awarded the Frolic Prize. In 2014, he was awarded the Royal Society Wolfson Research Merit Award, and many more. So without taking much time from you, so let me conclude by saying that he will be speaking on joint moments. Welcome to Kerala School of Mathematics, Professor Jon Keating. Over to you.
Well, thank you very much indeed, Professor Chakraborty, and thank you for that very kind introduction and for your invitation to participate in this workshop at the Kerala School of Mathematics. The Kerala School really does look like a splendid venture, and I do wish you all well in developing your mathematical activities there. I'm particularly pleased to be celebrating Ramanujan's birthday with you all. What a wonderful figure. We had a celebration a couple of years ago at the Royal Society for 100 years centenary of his election, and it's nice now to be celebrating his birthday with you all. So I shall be talking about joint moments, and I'll explain what joint moments are in a minute, but I'd like to start with some context for the work I'll be describing. So this context comes from analytic number theory, and it concerns the Riemann Zeta function. So this is a function defined when the real part of S is greater than 1, either by a sum over the natural numbers n, or as a product over prime numbers p. And it's this latter representation that makes the zeta function important, because the analytic properties of the zeta function encode information about the prime numbers. So for example, the prime number theorem and many other things that we know about the primes follow from analytic information about the structure of the Riemann zeta function. So the zeta function has an analytic continuation to the rest of the complex S plane, apart from S equals 1, where it has a simple pole. It satisfies a remarkable duality relation, a functional equation, which means that if you multiply it by pi to the minus s over 2 and gamma of s over 2, the resulting function is symmetric under s goes to 1 minus s. And it is worth noting that Ramanujan knew this and had proved this for himself using his own rather particular techniques. This played a very important part in his thinking. So he was greatly interested in the values of the zeta function at negative real values of s. He knew, for example, as Riemann also knew, that the zeta function has zeros at the negative even integers, -2, -4, -6, etc. But it has other zeros, infinitely many of them, which are not on the real S line. They lie in the complex S plane with non-zero imaginary parts. And in fact, these zeros are known to have real parts between 0 and 1. This is the critical strip of the Riemann zeta function. So somewhere in that strip, bordered by the lines real part of S is 0 and real part of S is 1. The zeta function has infinitely many zeros. And you'll all be aware, I'm sure, being mathematically fascinated people, that the Riemann hypothesis, which concerns these zeros, says that they actually all lie on the line which is the symmetry axis of that strip, so which bisects the strip. The line real part of S is 1/2. And this, of course, is one of the great problems of mathematics. So another way of saying this is that if we denote the zeros of the zeta function, the non-trivial zeros, the zeros that are not the negative even integers, if we denote those zeros by a half plus I tn, then these numbers tn are all real. So there's been a huge amount of interest in these zeros. We know, for example, that the Riemann hypothesis is true for at least 42% of the zeros of the zeta function. But progress on improving that fraction has become exponentially slow. So we make minor increments in that percentage, but we're still very far, for example, from proving that 50% of the zeros are real. The zeros Tn satisfy the Riemann hypothesis. We do know one very interesting fact, which I want to explain to you. And this is a remarkable conjecture. And there are theorems relating to this conjecture, which I'll explain in a minute, but the conjecture itself is a truly remarkable property of the zeros of the zeta function, if it's correct. And this is Montgomerys' conjecture. So this was made in 1973, and it says the following. It says one should compare the statistical distribution of the zeros of the zeta function, the numbers Tn, with the eigenvalues of a random unitary matrix. So what does that mean? Well, let's start with the zeros. The numbers Tn, which according to the Riemann hypothesis are all real, as n increases, these numbers have a logarithmically increasing density. And so we can define a new set of numbers Wn, which are the Tn's multiplied by 1 over 2 pi log mod Tn over 2 pi. And these numbers Wn have mean density 1. So the extra log in there stretches the zeros out and counterbalances the logarithmically increasing density to give a set of numbers with mean density 1. And we're going to look at the statistical distribution of these numbers Wn. In particular, we're going to look at the distribution of pairs of Wn's. And so if you look at the left-hand side of the equation, which is set out in Montgomerys' conjecture, we're going to form some function, which is arbitrary, restricted so that the sums converge, but that's a very minor restriction. We're going to form some function of differences between pairs of zeros. So we get the first capital N zeros, we form all pairs of them, and we form some function of the differences between the Wn's and the Wm's, and we sum over the first pairs formed from the first n zeros, that's n squared pairs, and we divide by capital N. So that's the zeta function side. And on the other side, we take a unitary matrix A, whose eigenvalues therefore lie on the unit circle. So I shall denote them by e to the I theta n. This matrix is of dimension n, so it has n eigenvalues. The angles theta n lie between 0 and 2 pi, so their density is n over 2 pi. So we'll form a new set of numbers phi n, which you get by multiplying the theta n's by n over 2 pi. So the phi n's, there are capital N of them, and they lie between 0 and capital N, and so their mean density is 1, just as for the Wn's. And so now, for a given matrix, we do the same thing. We form differences between pairs of the phi n's. This is now the right-hand side of the displayed equation. So the same function of differences of pairs of phi n's. We sum over all of the eigenvalues. There are n squared pairs of them. We divide by capital N, and now we average over the matrix A. And unitary matrices represent elements of the unitary group, and that group comes with a natural measure, the Haar measure, which is invariant under the group action, invariant under the action of all elements of the group. And that's the measure we use to average over matrices A. So we average over matrices A, and we compare that to the quantity we formed for the Riemann zeros. we take in both cases the limit as n tends to infinity, and Montgomery's remarkable conjecture is that the two sides will be equal to each other. So this means that if it's correct, that the Riemann zeros have very particular correlations which are the same as those of the eigenvalues of random unitary matrices. Now, this may seem like a rather abstract theorem, but it's of enormous practical importance because the average on the right-hand side, the random matrix side, can be computed. And this was done by Freeman Dyson in 1963. So the right-hand side can be evaluated to be the integral of the function f against some kernel, which is Dirac delta function plus 1 minus sine pi x over pi x all squared. So in fact, there's a very explicit formula. So this is the Montgomery conjecture. It's a theorem for certain functions f, in particular functions f whose Fourier transform has compact support lying between -1 and 1. And for functions f not of that form, it's a conjecture, but it's a theorem in many interesting cases, but not in full generality. Perhaps the best way to illustrate this is to show a plot of some data. So here are the points represent data for the Riemann zeros. This is for zeros up near the 10 to the 20th zero of the zeta function. And the line is the function 1 minus sine squared pi x over pi squared x squared. So you can think of this as the probability measured on the vertical axis, not normalized, that you find pairs of Riemann zeros with separation x. X is measured on the horizontal axis. So the Riemann zeros don't like to be too close together. As x tends to 0, the data and the random matrix prediction both tend to 0. But then this increases with x until you reach some sort of saturated oscillations. And the agreement's remarkable, and this is not even the best data. So all the data we have and all the evidence we have suggests that the Riemann zeros have a statistical distribution which really is the same as that of the eigenvalues of random matrices. And that's of huge philosophical importance, because one way to prove the Riemann hypothesis would be to find a spectral interpretation of the numbers Tn. For example, if the numbers Tn were the eigenvalues of some self-adjoint operator, that would prove the Riemann hypothesis. And what this conjecture and the numerical evidence I've shown you and the theorems that go with it indicate is that the Riemann zeros do behave like a sort of random operator, a typical operator. But that's not the story I want to tell you. I don't want to use this to try to understand the Riemann hypothesis. My goals are somewhat more modest, although not completely modest. I want to tell you about the moments of the Riemann zeta function. So I'm building my way up to talking about joint moments. They'll come later. I want to talk about moments right now. So the moments of the zeta function are what you get if you take the zeta function, take its absolute value, raise that to some power, 2 beta, and then average along the critical line to some height, capital T. And these have been very widely studied in analytic number theory. The study goes back to Hardy and Littlewood in 1918, who computed the moment corresponding to beta equals 1. So we have a theorem for beta equals 1. Ingham computed the moment beta equals 2. And actually, they're the only two cases where we have a theorem. So we've gone from beta equals 1 in 1918, beta equals 2 in 1926, and there's been no progress since in developing a rigorous asymptotic formulae for these moments. That's not for want of trying. There's been a great deal of work on these. We have bounds in various ranges due to Heath Brown, Ramachandra. We have Rudnick and Soundarajan. We have estimates based on certain other conjectures. So if you understand correlations between values of the divisor function, you can say something about these moments conditionally on that knowledge. And we've come a long way in the last 100 years, but still no theorems beyond beta equals 2. So how can we understand these moments? They're clearly difficult analytically. And as I've indicated, there are some heuristics surrounding these, but one wants as much evidence as possible. So the question is, can we understand the moments using ideas from random matrix theory? And this is an old story. I'll just briefly reprise it because the intuition that we get from this will feed into the thing that I really want to tell you later on about joint moments. So can we understand the moments of the Riemann Zeta function by looking at corresponding moments for random matrices? The intuition being that if the statistical distribution of the zeros of the zeta function matches the statistical distribution of the eigenvalues of random matrices, maybe we can say something statistically about the zeta function itself using some property of random matrices. And the idea is to compare the zeta function to the characteristic polynomial of a random matrix, because both have interesting zeros that conjecturally have the same distribution. So we'll look at this quantity Pn, it's the characteristic polynomial of the matrix A, and ask for its moments. And in this case, that means getting the characteristic polynomial, taking its absolute value, raising that to the power 2 beta, and averaging over the unitary group uniformly with respect to Haar measure on the group. And as I say, we're going to compare random matrix moments to the zeta function moments to see whether there's any matching. So how do you compute the random matrix moments? Well, there are the moments at the top. We're to average the modulus of the characteristic polynomial to the power 2 beta. And the characteristic polynomial is a product over the eigenvalues. So we have to average this product over the eigenvalues. And it turns out you can do that because there's a formula due to Hermann Weyl in 1944, which tells you how to represent Haar measure in terms of the eigenvalues. And this is the Weyl integration formula. So the Weyl integration formula gives you the formula in the middle, which is this multiple integral over representation for the moment. So now we have an integral to compute. It's an integral over the n eigenvalues, theta 1 up to theta n, and you see the quantity we want to average, and then the measure, which is represented by this factor measure there on the pairs of eigenvalues. So we have this multiple integral, and it turns out that this is an integral that you can compute exactly by some miracle, and I'll mention what that miracle is in a minute, but the answer that you get is that the moments of characteristic polynomials of random matrices are given by the formula at the bottom, which is a product of ratios of gamma functions. So that's an identity. So how do you evaluate this integral? Well, this is a famous observation of Selberg in 1941 and 1944. Selberg gave himself the challenge of generalizing Euler's beta integral, which you'll all be familiar with, which is the integral that I've represented there, which also is a ratio of a product of gamma functions and ratio of products of gamma functions. And Selberg realized that this integral does have a generalization, and that's the integral at the bottom there. And I won't go through the steps, but you can use this integral to evaluate the random matrix integral we wanted to calculate. Now, just as a historical aside, this really is a remarkable achievement of Selberg. He was working in complete isolation. This was, of course, the period of the Second World War, and he essentially had no contact with other mathematicians. He was in Norway at the time, and he wrote down this integral, which you could evaluate, And he wasn't aware whether or not this was known, and he assumed it would be. After all, people had had 200 years to come up with it. And so he wrote this paper, his original paper, in a journal for high school teachers in Norway, and he wrote it in Norwegian. So it was about the most obscure paper you could imagine. This is not a paper you would chance upon in the library. And in fact, the paper went completely unnoticed until 1980. It had not one single citation until 1980, despite the fact many other people had tried to compute this integral, including some of Selberg's closest colleagues. So Freeman Dyson spent nearly a decade trying to evaluate this integral and failed, and wasn't aware that Selberg had actually done this 20 years earlier. And Selberg had the office very close to Dyson. So it's a curious historical point. But anyway, Selberg eventually revealed to the world he'd computed this integral, and that's what allowed us to compute the moments of characteristic polynomials. So that product of gamma functions that you get from Selberg's integral has the property that if you divide it by n to the power beta squared, there's a limit as n tends to infinity, and it's given by a ratio of special functions called Barnes G functions. So Barnes was Littlewood's PhD advisor, and this Barnes G function generalizes the gamma function. For integer values of beta, this takes an even simpler form. If you take the limit is simply equal to a product of ratios of factorials. There's a very explicit formula for the moments of characteristic polynomials of random unitary matrices. And it's highly surprising that there's no a priori reason why this should be a rational number, but it is. And in fact, it has the general form that it's an integer over k squared factorial. Gk is some integer. And Gk has remarkable combinatorial properties. It appears in many settings. I'll give you one of them. If you take a k by k array of array, for example, a k by k chessboard, and you place the integers 1 through to k squared in the array, there are k squared boxes. So you put the integers from 1 to k squared in such a way that the numbers increase along each row and down each column, and ask how many ways are there to do that. The answer turns out to be precisely gk. So there's a remarkable combinatorial interpretation of these numbers gk that represent the moments of characteristic polynomials. So now, then it was a long time ago now, conjectured that the moments of characteristic polynomials should actually give us the answer for the moments of the Riemann Zeta function. So for general moments, we have that the moments of the zeta function should be the factor in blue, which just comes from random matrix theory, and then a factor in red, which I won't describe to you. That's an Euler product, so a product over prime numbers, which is very well known. Every number theorist would write that down immediately. So the problem factorizes as a bit coming from the primes in the A function, and then a bit coming from random matrix theory in the blue function. And for integer moments, the same thing. We have the Euler product for representing a function A, and the blue factor, which is this interesting combinatorial factor. So this was the conjecture. And now, having made the conjecture many years ago, there are many heuristic derivations of these formulae, at least in the integer case, based on information about correlations of the divisor function. So we can now justify these formulae or motivate them purely from number theory. But at the time, the only way we had to guess these formulae was random matrix theory. So it's the usual story that if you have the answer in the back of the textbook, it's easier to get the answer. And random matrix theory gave us the answer in this case. And then in the subsequent 20 years, we've come up with heuristic derivations of these formulae, reliant on conjectures around divisors of correlation function, divisor functions. So that's the story about moments. Now let me move to the main cast of characters in this talk. These are the joint moments. So we've known about moments, and they've been studied very intensively for 20 years. I now want to study the joint moments, which are moments defined in the following way. So let's get the Riemann Zeta function and multiply it by a function, e to the I theta of t, that makes the zeta function real when t is real. So from the functional equation, we know how to write down theta of t. And this was a function introduced by Hardy, and it's called, in many settings, the Hardy Z function. That's what it's often known about in many parts of the literature. So we're going to get the Hardy Z function, which is the Riemann zeta function multiplied by a function of modulus 1, which makes this real when t is real. So this is really just another way of stating the functional equation of the zeta function. And we're going to do the following. We're going to first of all take the moments, the modulus of z, and raise that to some power, 2k minus 2h. Well, the modulus of z is just the modulus of zeta, because they're the same up to a multiplication by a function of modulus 1. But then we're going to multiply by the modulus of the derivative of z to some power 2h. So the joint moments are the things in the middle there. So we get the modulus of z to the power 2k minus 2h and the modulus of z prime to the power 2h. So there are two parameters defining these moments, k and h. And the study of these joint moments goes back almost as far as the study of the moments themselves. So Ingham introduced them in 1926. And since the 1980s, there's been a great deal of activity relating to them, partly because information about the derivative of the zeta function, so the derivative of the Hardy Z function, if you like, plays very much into the methods that we have for estimating the fraction of zeros on the critical line. So Levinson's method gave 1/3 of the zeros being on the Riemann zeros line, satisfying the Riemann hypothesis, relies on knowledge of the value distribution of Z prime, and all subsequent methods do as well. So these joint moments are really very interesting because if we understood them better, the hope is that that would feed into better estimates on the fraction of zeros satisfying the Riemann hypothesis. But it turns out they're very hard to understand, much harder than the moments. And I think up until recently, that's not been at all clear why that should be the case. So it's clear that they have interesting formulae for them. So we do have, there are some values of k and h for which they can be evaluated. So if h is 1/2 and k is 1, then you get this formula at the bottom due to Conry and Gosch in 1989, that the average of mod z times mod z prime along the critical line of the zeta function is e squared minus 5/4 pi times log t squared, which I think is a beautiful formula. I'm sure it's a formula Euler and Ramanujan would have liked. But deriving systematic formulae for these things hasn't proved possible. And so obviously it was natural to wonder whether random matrix theory would help shine some light on the structure of these joint moments. So let's look at the joint moments of characteristic polynomials of random matrices. They helped us with the moments. Will they help us with the joint moments? So what's the analog of the Hardy Z function? Well, we get the characteristic polynomial P. It satisfies a functional equation too, just like the Riemann zeta function. And the functional equation there you can prove just from the fact that A is a unitary matrix. And in this case, the analog of the Hardy Z function is the function Vn, which I've shown you there. So once again, it's a function of modulus 1 times the characteristic polynomial, and the function of modulus 1 is completely explicitly given in terms of the eigenvalues. And this function V is real valued when theta is real valued, just like the Hardy Z function. So now the joint moments in this case are that we get the modulus of V and raise that to the power 2k minus 2h, and the modulus of V prime and raise that to the power 2h. And for these moments to exist, we need h greater than minus a half and k greater than h minus a half. Otherwise, the zeros of the characteristic polynomial, that is the eigenvalues, will appear as singularities of the joint moments. So it's only in this range, h greater than minus a half, k greater than h minus a half, that the joint moments exist. And we'd like to understand these, and the hope is that if we can evaluate the joint moments of characteristic polynomials, that will tell us about the joint moments of the Hardy-Z function.
Sorry, can I ask us a quick question? So the argument there, is it 0 or is it theta?
So in fact, you can put theta in if you like, but it is 0. That's because the unitary group is rotationally invariant. So part of the unitary group is simply multiplication by e to the I theta, which just rotates the spectrum. So you can evaluate these joint moments anywhere and they give you the same answer.
Okay. And the second question is the derivative in V prime, is that with respect to theta?
Yes, with respect to theta.
So that's what plays the, I mean, because I was just wondering, because I thought theta was related to Wn, which was not quite the same as T, so.
Well, no, so the theta ends are like the Wn's. Theta is like T. So theta is the variable in the characteristic polynomial, and by varying theta, you go through the zeros of the characteristic polynomial, which are the eigenvalues denoted theta n.
Okay. Okay, thanks.
So yes, derivative is with respect to theta. And you can evaluate this at any choice of theta, and I've just chosen to evaluate it at theta as 0. So these joint moments of characteristic polynomials have been much studied as well. They were introduced by Chris Hughes about 20 years ago, and been very intensively studied since to try to evaluate them. But that's proved quite difficult. Chris Hughes conjectured 20 years ago that these joint moments should scale like n to the power k squared plus 2h when n is large. So put another way, if you divide the joint moment by n to the power k squared plus 2h and take the limit as n tends to infinity, you should get a function which is finite. The limit should exist, finite and non-zero, and in the range where the moments exist. And so the goal is to identify this function f of k and h. The limit as n tends to infinity of this ratio of the joint moments and this power of n. And this is exactly what we were doing for the moments. And there we found it relatively straightforward. We used the Selberg integral. And there are many other ways to get the answer for the moments. But for the joint moments, it's proved a lot more difficult. So Hughes conjectured that if we did have this function f, then the joint moments of the Hardy-Z function should be given asymptotically by a similar formula to the moments. So A of k, that's the Euler product, that's the same arithmetic factor that appeared for the moment. F of k and h, which it should come from random matrix theory, and this power of log t, which is k squared plus 2h. So that was the conjecture that Chris Hughes made, and this has led to a lot of interest in this function f of k and h. Unfortunately, it's proved extremely difficult to evaluate this function. So Hughes proved, first of all, that that was the right scaling with n. Okay, the joint moment scale like n to the power k squared plus 2h for integer values of k and h. But the proof he came up with didn't lead to a tractable formula for f. It was a limit of some sequence of determinants and didn't give a formula that one could really use terribly easily. There is a sort of representation theoretic way of getting at these joint moments. And this representation theoretic approach uses the fact that the symmetric polynomials, Schur functions, represent the irreducible polynomial representations of the unitary group. And so you can write everything in terms of a combinatorial sum involving Young tableau. And in fact, it's this approach that leads to the very nice combinatorial interpretation of the moments. But for the joint moments, it turns out that this is rather more complicated. It's not simply counting k by k arrays with the integers from 1 to k squared in the boxes and some slightly different rule for how the integers should be arranged. Here, it's a much more complicated expression. There has been progress. So Wynne used this approach to show that for k is 1 and h is 1/2, you indeed get this beautiful formula e squared minus 5 over 4 pi. So he proved that in random matrix theory, you get exactly the same magical number. But finding other numbers by this approach hasn't proved terribly successful. It does show, this approach does show that for h an integer, that the structure that one gets for the joint moments is that you have this ratio of Barnes G functions multiplied by a rational function of k, and the first few could be computed. But again, using this combinatorial approach, it's not been possible to go terribly far with computing these rational functions. And so this has sort of ground, progress has got slower and slower via this approach, and it's not been clear why it's so much more difficult. So all these approaches give you the right scaling with n, but don't give you very tractable formulae for f of k and h, except in a few cases corresponding to small k values of k and h. And it's not been clear why the problem's so much more difficult than the moments. So this is now where I want to get onto some more recent, some progress that's been made recently, which has made it clear that the joint moments are very considerably more complicated than the moments. And this wasn't at all obvious 20 years ago. And the right way to describe them doesn't come from formulae like the Selberg integral gives you, products of ratios of gamma functions, but much more complicated transcendental objects. So really, we spent 20 years looking for simple formulae, but it turns out the formulae, the right formulae, the correct formulae, are necessarily more complicated and have a transcendental flavor to them. And I want to tell you what that flavor is. So I'm going to tell you about a connection with Penlevet equations. So the Penlevet equations are a set of 6 nonlinear second order ordinary differential equations, which are exactly integrable. So these were classified just over 100 years ago by Paul Penlevet. So it's easy to classify nonlinear equations, ODEs that are first order, which are integrable. And that was done sort of by Fuchs and others in the 19th century. And in the early 20th century, nonlinear integrable ODEs that are second order were classified by Penlevet, and there are 6 of them. They depend on certain parameters. And we're going to see that one of those differential equations plays the key role, actually 2 of them, in describing the joint moments of characteristic polynomials. And so conjecturally, the joint moments of the Riemann Zeta function. So to set this up, I'm going to show you some formulae which may look a little scary, but hopefully not too scary. And the details don't matter. When I get to the important formula, I shall indicate the formula you do need to pay some attention to. So we're going to define L, which will be a generalized Laguerre polynomial. So it's given by a generating function, which corresponds to differentiating the simple function t to the power alpha plus n times e to the minus t n times. and that gives you a set of polynomials which are represented by the sum at the top there. The sum from j is 0 to n. So these polynomials are classical. We're going to define a function k, which corresponds to differentiating the function epsilon over epsilon squared plus y squared n times. And then there's a very nice expression, which you don't need to remember due to Brian Wynne, which says that the joint moments of characteristic polynomials can be represented as an integral, an infinite integral, minus infinity to infinity, of the function k, which I've defined there for you, multiplied by a determinant where the entries in the determinant are generalized Laguerre polynomials. So this looks appealing, but what is this determinant of Laguerre polynomials, and how do you evaluate this integral over y? So Wynne got this far and then analyzed this in a few simple cases. But the question is, what's the general structure for determinants of Laguerre polynomials, and can you evaluate this integral? So I'm simply going to give you the answer, which is that determinant of Laguerre polynomials can be written as a function h of k, and h of k is itself a determinant where the elements of the determinant are contour integrals. So this is easy. This is simply using the fact that you can represent the Laguerre polynomials as contour integrals. So far, I've really not done very much at all. This is just a convenient way to state the theorem, the main result of the theorem, which is that this function h, this determinant of contour integrals, which represents the determinant of Laguerre polynomials that we need to evaluate the joint moments, this determinant of contour integrals satisfies one of the Penn-Levy equations. And this is not at all obvious, and wish we'd known this 20 years ago, but there you go. This has taken a long time to tease out. So the right structure for understanding the joint moments is to represent them in terms of determinants, and then to recognize that those determinants satisfy second order nonlinear integrable ordinary differential equations. And so the equation that I've given you is there. It's actually the fifth equation in Penn-Levy's classification of integrable second order nonlinear ODEs, and there it is. So that's the equation which you need to solve, and you need to solve it with a boundary condition, which is the condition that the solution you want behaves, as I've indicated at the bottom, as x tends to 0. So I don't know how much sort of solving ordinary differential equations you've done, but now we really are home and dry, because you simply put in a series solution and you can generate solutions, as many solutions as you like, in microseconds using any package you want, or do it by hand if that's your bent. So from this representation in terms of Penn-Levy equations, you can generate these functions, the joint moments. They're given in terms of this ratio of Barnes G functions multiplied by various rational functions of k and n. And you can generate tens of thousands, millions of these if you want from the differential equation. And you see they have the general structure that had been predicted. They're a ratio of Barnes G functions multiplied by rational functions of k when h is an integer. And if you take the limit as n tends to infinity, you get the right limit. The scaling is with n to the power k squared plus 2h. And then you get these rational functions that remain, which now have a very nice simple structure. So one can solve this problem now. We can calculate joint moments, as many as you like, at least for integer values of h. And you can actually prove that structure persists for all values of h by looking at the asymptotics of solutions of this Penlevet equation. So this is an area of asymptotic analysis of differential equations. You can study the solutions of this differential equation, the Penlevet 5 equation, when n tends to infinity. And what you get is that the mysterious function f of h and k, this function that describes the n to infinity limit, is the derivative of the exponential of an integral of a solution of a different Penlevet equation, in this case, the third Penlevet equation, the third on the list of Penlevet's classification, which is the differential equation given in the middle line there with these initial conditions. So we now can prove the Hughes conjecture for integer values of h and for all k greater than h minus a half, using a connection with this Penlevet's classification of integrable ordinary differential equations, second order. And so this solves the problem, at least for integer h. But can we now do non-integer h? Well, it turns out that we can. And this is a rather recent result, which I'll describe here. So now we'd like to go from doing integer h to all general non-integer values of h and k. And once one sees the connection with Penlevet, you can guess the answer, and now we've been able to prove it. So here's what the answer looks like. This is related to a famous construction called the Piccrel measure in probability theory. So if we take a set of points x1 through to xn, these are all real numbers and they're ordered, you can place a measure on that set of points. So this is a point process, if you like, in the language of probability theory. And the measure you place on that set of points is the measure given in terms of this middle equation there. So it resembles the Weyl integration formula. It has the same van der Monde factor that the Weyl integration formula has, but it has this extra factor here, which has the structure of a sort of Cauchy distribution. And there's a normalization constant, which I've given you there for completeness, but you won't need to remember that. So all you need to know is, here is a measure which is famous. It's got a name called the Piccrel measure, and it's a measure on a set of n real numbers. And I've given you a formula for the measure. Then you can ask, given the Piccrel measure, what's the average value of that set of numbers? Does that exist? And it turns out that it does. The average of the set of the numbers x1 through to xn converges in distribution as n tends to infinity to a limiting random variable x of s, which, and this was proved by, goes back to work of Vershik in the 1990s and Borodin and Olshansky in the early 2000s, and a very, very beautiful piece of work by Chu sort of settled this completely in 2017. So this is a very well-known problem in probability and in representation theory. This random variable x of s appears very naturally in the theory of the infinite dimensional unitary group, for example. But I won't say more about that here. So it's known in the theory of Piccrel measures that the average of the set x1 through to xn exists and converges in distribution as n tends to infinity to a recognized random variable that's proved to exist. Then very recently, we've observed that, in fact, the joint moments of characteristic polynomials for any choice of k and h, for integer and non-integer, can all be represented in terms of this random variable x of s. So the Hughes told us that if you get the joint moments and divide by n to the power s squared plus 2h, you get a limit, and we can prove that that's true. Now, for all s and h in the range where the moments exist, and that limit just corresponds to the moments of this random variable x of s, which I mentioned, described on the previous slide. And so this proves the Hughes conjecture for all for all choices of the two parameters in the range where the joint moments exist, and gives you a prescription for how to compute them. They're just the joint moments of this random variable x of s that's related to the Piccrel measure. So how do you prove this? Well, the first key ingredient is to write the joint moments in terms of the Piccrel measure, which you can do. And then you find that the joint moments correspond to the moments, the 2h moment of the absolute value of the average of the variables x1 through to xn. So Borodin and Olshansky and Chu proved that the term inside the absolute value has a limit in distribution as n tends to infinity. Do the moments, and that's what we had to prove. So we had to prove convergence of the moments when n tends to infinity and show that they converge to the 2h moments of the random variable x of s, as one might hope. But that has to be proved. Now, the difficulty is that the numbers x1 through to xn can be positive or negative, and roughly half of them are negative and half of them are positive. And it turns out that if you take the absolute value inside the sum, then everything diverges horribly and you can't prove anything. So all the standard techniques for proving convergence of moments fail if you approach this naively, sort of as an analyst, and try to bound the absolute value of the sum by the sum of the absolute values. That simply doesn't work. But these numbers xn are eigenvalues of a matrix, and so the sum of them is simply the trace of that matrix. This is the matrix which has the Piccrel measure, so which supports the Piccrel measure. And so we know another formula for the trace of the matrix. It's not just the sum of the eigenvalues, it's the sum of the diagonal entries. And if you remember that fact from elementary, from either high school or first year linear algebra, then you can compute these moments because the diagonal matrix entries have a form that one can analyze. And I won't go through the details, but we can prove then, using that fact, that all of the moments that we want to exist do exist. And so this joint moments exist for all choices of the variables x1, of the two variables on which it depends. So this means two things. It means that we now have, after a long time, computed the joint moments of characteristic polynomials, of random matrices. And the reason it was difficult is that they're not given by simple formulae. They're not products of gamma functions. For integer values of the variables, they're given by solutions of Penn-Levy equations, and those are transcendental functions which can't be represented in terms of finite combination of sort of elementary classical functions. These are genuinely new class of functions, the Penn-Levy transcendents, and they are what they are. So the joint moments just are solutions of a Penn-Levy equation, and that's the best you can say. They're not Hermite polynomials, they're not Legendre polynomials, they're not gamma functions. They represent solutions of Penn-Levy equations, and that's the best that one can say. And for non-integer values of the arguments, we have a formula now which relates them to the moments of this random variable that appears in the theory of the Piccrel measure, and where we can show that these moments exist. And so we have established the Hughes conjecture, which means that we can put these formulae into the Hughes conjecture for the Hardy Z function. And so now we have a formulae for the joint moments of the Hardy Z function for any choice of the variables S and H on the left-hand side. For integer values of S and H, the joint moments of the Hardy-Z function are given in terms of the solutions of Penn-Levy equations. And for non-integer values, they're given as moments of this mysterious random variable related to the Piccrel measure, the moments of the random variable x of s, the average value of the points in the point process. So we now have the answer in the back of the book, and it's not an answer that we were expecting, but this is what nature has given us, at least if you believe the connection with random matrix theory. So it's certainly the answer for the joint moments of characteristic polynomials of random matrices. Conjecturally, it's the answer for the joint moments of the Hardy-Z function, if you believe this connection between the zeros of the Riemann Zeta function and random matrix theory. This is the conjecture you would make. And it suggests that the Riemann Zeta function has structure that we never anticipated. So we were slightly misled by the moments, which have simple formulae in terms of ratios of gamma functions, in terms of combinatorial sums involving placing the numbers from 1 to k squared in a k by k array and counting the number of ways of doing that, counting Young tableau. The joint moments are just much more mathematically intricate, and that makes them difficult, but it makes them fascinating. And I think that this suggests structure that we never anticipated and that really now one should investigate further. So the question would be, having made the conjecture, having seen what to put into the Hughes conjecture, we now have a very precise conjecture to make for integer values of S and H. The joint moments of the Hardy-Z function are given in terms of solutions of Penn-Levy equations, and for non-integer values in terms of this random variable. And so the challenge must be to try to establish this, prove it if you like, or at least see heuristically why it's true, purely using number theoretic techniques, using properties of correlations of the divisor function, for example, or probably correlations of the divisor function and the von Mangold function, because we're dealing with not just moments of powers of z, but also powers of z prime. So the von Mangold function is also likely to be important here. And this suggests that if you look at joint moments of the divisor function and the von Mangold function, these should be in some way related to solutions of Penn-Levy equations. But I really can't see, I don't have even the beginnings of an idea of how you would see that connection. I should say this conjecture matches every theorem that's proved in the literature. So the choices that I indicated were, we know the joint moments of the Hardy-Z function. So for example, when h is a half and s is 1, we can now recover that famous constant e squared minus 5 over 4 pi from solutions of Penn-Levy equations. So everything matches with everything that's been known to date for the last 100 years, matches this connection with Penn-Levy. But seeing in general that is the right general formula for these joint moments is wonderful, I think, in my view, as an open problem. So it'd be nice to try and justify this using correlations of divisor functions, or the standard approaches one would take in number theory. It would be very interesting to explore the consequence of this for zeros of the derivative. So does now understanding the role that Penn-Levy equations play would that allow us to prove a greater fraction of zeros of the zeta function lie on the critical line? Well, I think I think that's an open problem, and I think we're just in the beginnings of thinking about this. But I think it is. I commend it to all of you as a problem to think about further. And as I say, to explore the arithmetic origins of the Penn-Levy equation. So it should be that the solutions of the Penn-Levy equation I wrote down should appear using purely number theoretic techniques, using the divisor function, von Mangold. But as I say, I haven't even the beginnings of an idea of how one would go about showing that. which makes it a problem I'm very interested in. So I think it's a problem that I'd like to think it's a problem Ramanujan would have been interested in too, and probably would have seen through rather more quickly than we have. I'll stop there. Thank you very much indeed.
Thank you very much, Professor Jon Keating. It's a wonderful lecture connecting these joint moments of zeta functions with these differential equations, mainly differential equations, and throwing in a lot of questions to the audience who are attending today. So there will be some questions, and I will be first looking at this audience here in the seminar room. So is there any question here? No questions. This is talking about Riemann hypothesis. So if there are any questions from the Zoom participants, they can unmute themselves and can ask questions to Professor Jon. And what about this YouTube chat questions? Is there any, Srijit?
No, sir. There are no questions in YouTube.
Hello, can you hear me? Can you hear me?
Yeah.
I have a question about the connections between whatever you have said today with the Selbach zeta function. Does it have any connections at all with the Selbach zeta function?
So, yes, I've not spoken about that. That's an extremely interesting question. So one would believe that the moments of the Selbach zeta function, at least in certain particular cases, for the Selbach zeta function for surfaces of non-constant negative curvature, one would believe that similar formulae should hold. So that one would believe that in those cases, the eigenvalues, the zeros of the Selbach zeta function, so the eigenvalues of the Laplacian on the surface in question, there's a general set of conjectures that they would also be distributed statistically like the eigenvalues of random matrices. From that, you would infer or guess that the moments of the Selbach zeta function should be described by the moments of characteristic polynomials of random matrices, and so formulae like the ones I've shown should apply. I think people haven't worked those cases out precisely, but it could be done and would be interesting to do.
One more question.
Yes.
The representation theory of the unitary group plays an important role in the sense of the Weil integration formula and so on.
Yes.
And in the case of the Selbach zeta function, the connection is also with the so-called class 1 representations of the group SL2R.
Yes.
So in that case, could that, is there any kind of analog with whatever you have said?
So I actually don't think it'll be with the representations of SL2R. I think you're quite right that underlies the Selbach zeta function. But I think that the groups that will appear are also either the unitary group, the orthogonal group, or the symplectic group. So the group you mentioned does indeed generate the dynamics on the surface, and so gives you the lengths of the closed geodesics. But the eigenvalue distribution will be governed, we believe, it's a conjecture, just by the orthogonal group, the unitary group, or the symplectic group. The story is a little complicated for the Selbach zeta function, so I don't want to make an absolutely precise statement, because to do so, I'd have to write things down that I don't have the opportunity to do. But that's the gist of the story, that in fact they won't be much different to the cases that I've been considering here. I think what's very interesting, I just realized your question really is exceedingly interesting, because if you could look at the joint moments of of the Selberg zeta function. Of course, for the Selberg zeta function, in many interesting cases, we know the Riemann hypothesis because the zeros are the eigenvalues of a self-adjoint operator, the Laplacian. And so we know that all of the zeros lie on the critical line, and it would be a natural way to try to test these methods to prove that a certain fraction lay on the critical line. So of course it's unnecessary for the Selberg zeta function because all of the zeros we know lie on the line. But if you assume that you didn't know that, could you use joint moments of the Selberg zeta function to prove, say, 100% lay on the line? I actually don't know the answer to that, and I think that would be very interesting to explore.
One last question, please.
Yeah.
The
Yes, sir.
asymptotic formula for the zeros, for the non-trivial zeros of the zeta function, gives you some topological information, the genus of the compact Riemann manifold associated with the group modulo gamma, which is the discrete subgroup, or rather the upper half plane modulo gamma. But,
Yes.
I mean, is that also related to number theory?
Certainly, yes, absolutely. There's a very strong connection with number theory, especially if in the arithmetic case, which is the one you were describing. So there's a very strong connection with algebraic number theory, and I agree that it's an interesting case to study further. We've not gone in that direction.
Yeah, so if there are no more questions, let's thank Professor Jon Keating once more for this wonderful talk. And thank you, sir. Hope to see you here when the situation normalizes. It's a beautiful place in Kerala, southern part of India. And so we are planning to have it on a yearly basis. So this particular conference, so I would really hope that most of the speakers we got this time certainly would like to, we'll be able to have them here. It would be a wonderful opportunity for this school here. And thank you so much, sir. And for
to visit you, and I should enjoy that very much when the opportunity arises. And I wish the school well, but I wish all of you well mathematically and in terms of the health crisis currently.
Yes, same to you, sir. Thank you so much.
Thank you very much.
This was the last lecture for the conference, and let's give a big hand to all the speakers who spoke for our conference. And we will be gathering soon at 5 p.m. for the validation.